and welcome to this session. My name is Simon Ritter. I'm the Deputy CTO of Azul, and what I'm going to talk about today is AOT or JIT, faster startup or faster code. And the idea really is to look at the alternatives that we have available to us, and specifically from a microservices perspective of how we can deliver performance and what the performance characteristics that we're looking for and what the challenges are in terms of that. As a quick little bit of housekeeping, in terms of questions, I'll be very happy to address those, but because of the way that my presentation is structured and so on, I'd like to leave that until the end of the presentation. So if you do have questions, you can type them into the chat box, and I'll look at those at the end of the presentation. And obviously, if you've got questions as well, we can deal with those live at the end also, but I'll be doing that at the end. Okay, so let's get started then. The first thing we need to understand is that if we're using Java, we have a JVM, Java virtual machine, and that has specific performance challenges of its own. Now, Java is a very high performance language. It's a very high performance platform. And we've seen over the last 26 years that it has scaled very well to very large workloads. It's really one of the reasons that many people choose it for internet scale applications. And so, you know, people like Salesforce, people like eBay, they use Java as the runtime for their engines. But there are certain things that we need to consider when we're thinking about how to deploy Java and the best performance that we can get from that. The first of those is latency. And what I mean by this is the delay that we might get in terms of being able to respond to a request from our user. Now, that's latency in terms of the virtual machine, not of the application code. So we're considering what the JVM does here. And really the biggest consideration that we have there is garbage collection. JVM provides a managed runtime environment. That's very good. It's very powerful. It means that when we want new objects, we simply instantiate them. We don't worry about where that space is in the heap. And then we let the JVM deal with figuring out when we've stopped using objects and reclaiming that space for us. That's garbage collection. I'm sure everybody who's done any Java programming is familiar with that. And the impact of garbage collection on latency can be very large. If you look at a lot of the algorithms that we have used in the past, the idea of having to pause application threads in certain phases of the garbage collection process. So when we're marking, identifying which objects are still in use, we need to pause potentially for that. When we're relocating objects within the heap to eliminate fragmentation, to avoid inconsistencies of data, we pause the application threads to do that. That can introduce latency. But there's more to it than that. There's also the issue of JIT compilation. If we're running certain methods very frequently and the JVM decides that it wants to compile those, it may pause that thread that's doing the work whilst it does the compilation. That can introduce latency as well. So that's one of the things that we certainly need to consider. The second thing we need to consider is the idea of the throughput. So how many transactions per second can we deal with in a given JVM? If we're running in the cloud, we've provisioned a certain number of cores, we've provisioned a certain amount of memory. How many transactions per second can we deal with that? And that's going to depend to some extent on the code that we can generate with our compiler. Now, again, whether it's static, whether it's dynamic, but the optimizations that we can apply to the code that we have are going to determine how quickly we can run that code. More heavily optimized, the better we're going to do in terms of throughput. And then the last thing that really is very specific to the JVM environment is how quickly we can make a particular service or a particular application available in terms of its performance level. This is what we refer to sometimes as the warm-up time. And because we're using JIT compilation in the JVM, we start off in interpreted mode, we're taking bytecodes, we're converting those into the necessary instruction set for the platform we're running on. Then, as we notice methods being called more frequently, we then compile that using the C1 compiler, very fast compiler, but not optimizing. Then, once that method gets used more and more, we recompile using the C2 JIT compiler, heavily optimized based on profiling information. Now, that takes time, And the problem we face is that when we want to do the application again, or if we're starting a service, then we face the same issue of going through that whole warm-up phase again. So these are things specific to the JVM. Now let's have a little look at how things are slightly different in terms of the microservices world and additional challenges that we might have. If we look at a typical architecture of a microservice-based application, this is the kind of thing we're going to see. We're moving away from a monolithic application where you have simply one process that does everything. Now what we can see is that we can break that monolithic application into a number of services, have those linked together through well-defined interfaces. We can use something like Kubernetes to orchestrate the different services and understand how information flows through there. But if we look at this diagram, what we can see is we've clearly got a number of microservices involved. And one of the true advantages of taking this approach is that we may find that one of our services becomes a bottleneck. That may be a service that we use for lots of other parts of the system. Let's say it's credit card transaction processing, and that becomes a bottleneck, meaning that the whole system slows down. In a monolithic approach, we're very restricted in terms of what we can do to address that. Really, the only thing we can do is to throw more resources at the whole application. So more cores, more memory. And that can be very inefficient because we're throwing that at the whole application when it's only a small part of it that we really need to improve the efficiency of. In a microservice architecture, this is the powerful thing that we can do, because as long as we design our services correctly, we can say, instead of having one instance of that service, let's multiply it up, spin up new instances of that service, use those for different parts of the rest of the system, and then distribute the load across that. So rather than having one instance, now we've got three. That means that we can handle more transactions through those three instances. That reduces the bottleneck and improves the overall efficiency of our application. So that's obviously a very big advantage and makes life a lot easier for us. But of course, we have to be careful in terms of our design, because if we want to spin up new instances of a service, we need to think carefully about how we're going to deal with state in that case. So do we have the state external? Do we keep it internally and then manage that in a particular way? But that's something that we do need to think about. The other thing that we need to think about in terms of microservices, and particularly when we're dealing with Java microservices, is the overall effect for our users. So our users on the left here are interacting with whatever it is, our application that we've developed. From their perspective, they may be using a web browser, they fill in some form and they click send. And what they expect is that transaction to be handled by our system as quickly as possible. And their interaction is purely with the whole system. But when we look at the way that transaction is processed within the architecture, what we'll find is quite logically that there are a number of microservices being involved. So we'll flow from one microservice, that will call another microservice, that will call another microservice, and so on. Specifically, when we're using Java microservices, we need to think carefully because, of course, the latency, garbage collection effect that we will see is going to become cumulative. If we've got three different microservices involved and all of them start doing garbage collection, potentially at the same time, maybe different times, but that could be a cumulative effect on latency. Overall effect for our end user is going to be less performance than if we had a single service that was doing garbage collection only once every however many seconds or so on. But when we have three services involved, that cumulative effect becomes more significant. So if we look at those microservice performance challenges and kind of relate them back to what we've already talked about, first is, how do we spin up new instances? And how long does it take to do that? Because if we need that responsiveness, if we need to be able to adapt dynamically to changes in load, we don't want to be waiting, tens of seconds, minutes for a new service to come online, because that won't really help us in terms of addressing the load at that point in the user's experience. So how long does it take to start up a new instance? And that also may include how long it takes to provision a new cloud instance, which could be far longer than it takes to run up the new service. How long does it take to reach that full transaction processing speed? comes back to what I said about warm-up time in a Java application. So even though you might spin up the service very quickly, it may take quite a time for that service to then reach its full transaction potential. And that obviously doesn't really help us again much in terms of the overall performance of the application. That warm-up time is also much more relevant if we look at the kind of extreme forms of microservice where we're dealing with serverless computing or AWS Lambdas, where we're really just dealing with a function. So very quick, start it up, deal with that function, stop the service. Warm-up time, garbage collection, all can be very significant there. Throughput. Talked about that in terms of the JIT compilation, but from a microservice point of view, the transaction processing capability that we have for a particular service is going to determine how many of those services we're going to need to provision. If we can deal with a higher number of transactions per service, we'll need less services to handle the same number of users, the same number of requests. Lower throughput means a higher number of instances. And when we're dealing with a cloud environment where it's a utility pricing model, the more instances we have, the more we're paying, then throughput, higher throughput will mean less cost in terms of the overall effect of our application. And then finally, latency, as we've already kind of mentioned, both in terms of the JVM and also from the microservice point of view. This will, again, impact on how many instances of an application or service that we require. And we could actually reach an extreme situation. If we have a particular service that needs to do garbage collection and that GC pause becomes very long, then the rest of the system might think, oh, that application service has gone offline. And so it then goes through the sort of, okay, we'll start another instance of the service, we'll restart that service. And that sort of thing is also going to be very detrimental in terms of the overall performance of our application. So there's lots of things that we need to consider when we're designing and building a microservice Java-based application. Okay, let's talk a little bit about AOT and JIT and the differences between these. So the first of these that we need to consider is the idea of ahead of time compilation. And let's look at that in terms of Java. If we take our Java code, we can compile that directly into native instructions. In the same way that we would with C or C++ or Go, we can simply take the source code, run the compiler, and generate code for, let's say, Windows running on an Intel processor or Linux running on an ARM processor. Now that's good from the point of view of being able to provision services and being able to start them up, all that sort of thing. But there are a number of things that we need to consider that we will lose from that. First of those is the obvious portability. With bytecodes and a virtual machine, it means we take the same class files, the same jar files, and we can deploy them wherever we like. We don't care about whether it's Windows, whether it's Linux, whether it's ARM, whether it's Intel. All runs in exactly the same way because we're using the JVM. So we would lose that portability. Now, that in itself might not be too much of an issue because you're going to be targeting a cloud instance that's going to be running Linux, you're running on an Intel processor, so why not just compile directly to that instruction set? But there's more to it than that. And from a performance perspective, we need to think that even though you're running on, let's say, an Intel architecture, do you know specifically which micro architecture you're going to be using? Obviously, the Intel processors have developed over time, and part of that is including more instructions. Good example of that is the AVX instructions for vector operations. Very wide registers, single instruction, multiple data. If you want to get the best possible performance out of your code, what you really want to do is compile to the optimum level of instructions that you have. So if you're running on the most modern processor, you've got AVX 512. If you've got an older processor, you may only have AVX. Now, do you compile your code for the lowest common denominator? Do you say, well, okay, I don't know exactly which version of the processor I'll have, so I'll just compile to AVX, only got 128-bit register, versus if I know I've got the most modern one, it's 512 bits. So much better in terms of vector performance. So this is the kind of thing that we do need to consider is how do we compile? Do we go for, very, very specific microarchitectures? The other thing that we need to think about when it comes to static ahead of time compilation of Java code is that we're doing static analysis of the code paths. We're looking at the code purely based on what the source code represents. We have no idea of how that code is actually going to be used at runtime. So we can simply say, okay, we will compile based on this, and we don't know how it's going to be used when the application runs. Now, certainly there are techniques that can make that better. And there's a technique that's been around for decades called profile guided optimization. You run your application, you collect some information about how it's being run, and then you feed that back into the compiler, recompile it, knowing now something about what happens at runtime. But it's still static, meaning that you've taken a view of how that application runs at that particular point in time, but you haven't got the ability to change if your application changes. So sudden increase in the number of users choose to do something different, that's going to affect the profile. So we're really kind of fixed in terms of what we do with our static compilation. The other thing that's very important from a Java perspective is that Java is a dynamic language. Now, I don't mean from typing, it's statically typed, but it is dynamic in the sense that we can load classes at runtime. Very possible, it happens a lot in different frameworks. And that limits us in terms of how much optimization we can do. One of the most common things for a compiler to do to optimize is method inlining. Rather than creating a stack frame, calling a method, executing the code, and then popping the stack frame off, you simply say, well, if it's in a loop, what I'll do is just take the code of that method, put it into the body of the loop, and then avoid that pushing and popping of stack frames. That's all good, except if you don't know precisely which method is going to be called in that loop. If at runtime somebody loads a new class and the method that you think is going to be called is actually replaced with a different one, then you can't inline that method in the same way. So you can't use as aggressive method inlining in your Java code. So static compilation is very much restricted in terms of that method inlining, and speculative optimisations that I'll talk about in a moment are a very, very big thing from the point of view of how to optimize code for the best possible performance. And then also, if you are going to statically compile Java code, how do certain things that the JVM takes care of actually happen? So how do you deal with garbage collection? There's got to be something that deals with that in your statically compiled code. Just-in-time compilation. Okay, this is the opposite approach. This is the idea of what the JVM does. So rather than compiling before, we run the application, we let the application run, we count how many times a particular method is called, we look for those hotspots, hence the name of the JVM, find the methods that are being called very frequently, and compile those into native instructions when we need them. As I said, that happens in two stages. We go through the C1 compiled code, where we compile the code very quickly, but we don't apply a lot of optimizations. We then gather profiling data about the way that method is being used, so that when we decide to recompile it with C2, we can actually use more optimizations and take advantage of that profiling information to tailor the code to work with the way that method is being used. Obviously, if we're doing this at runtime, we have a precise view of what is happening in the application, and that will include all the classes that are currently loaded. That's great because it does mean that when it comes to method inlining, we do know exactly which method is going to be called at a particular time, and we can inline that. Should somebody then load another class and affect that, we can dynamically change the code. We can say, okay, now that method is invalid, throw away that code and recompile it. We're also able to use speculative optimizations. This is essentially saying that we look at the way the code has run up to this point in time, and we make the assumption that having run that way, it will continue to be used in that way in the future. And let's optimize based on that approach. Very powerful, very useful technique. The downside of JIT compilation is it involves doing a lot of extra work whilst the application is running. If we use static compilation, we do all of that compilation before we start running the application on the machine. Now what we're doing is we're saying, well, we'll run the application, but we'll also compile bits of code as it's doing it. That's going to reduce the number of cores that we have available for threads in the application itself. So that will potentially degrade throughput whilst we're going through the warm-up phase. Once we've got to the point where it's warmed up, we won't be compiling any more methods, so this isn't an issue. But during that warm-up phase, it can, again, degrade throughput. Talk a little bit more about speculative optimizations. These are, as I said, a very powerful technique. And this is an example that I put together to show how that can work. A little bit contrived, but it is representative of what can actually happen in code. I've got a method called compute magnitude, and it takes a parameter called value. What I'm then doing is using a conditional statement, and I say if value is greater than 9, then I want to compute the bias that I'm going to use using my value. So I'll call a different method, return some bias value, and then use that in my code. If the value is not greater than 9, then I simply set bias to be 1. And then, having determined which bias I want to use, I return the log base 10 of bias plus 99. If I profile this method, what I can do is I can actually count how many times the code goes through each branch of the if statement. What I might find is that all the time I'm going through the false branch of that if statement, and I never go through the true branch. Okay. If I understand that, then the compiler can optimize accordingly. What it can do is it can actually change the code, and it can do this because now we know that bias is always going to be 1 if we don't have a value that's greater than 9. So if we assume that bias is always going to be 1, we're always going through the false branch of that statement, then we can eliminate some of the code. We know that 1 plus 99 is 100. We know that log base 10 of 100 is 2. So let's not bother doing all that computation. Let's just return 2 because we know that will work so long as the value isn't greater than 9 and bias is 1. Now, obviously, to fulfill the contract with the code that we've written, we must still deal with a situation where we do get a value that's greater than 9. In that case, we need our if statement here, which says if value is greater than 9, do an uncommon trap. Now, uncommon trap is where we say, oh, we have assumed that the code is going to work this way. That is wrong. So the uncommon trap will then throw away that code and say, right, we must return to interpreted mode, and then we must recompile based on the fact that we could go through either the true or the false branch, and so we get more complicated code. So we still maintain the ability to handle all values, but so long as we don't exceed 9 in terms of our value, then we get better performance because we're eliminating all of this code. So that's the real benefit of speculative optimizations. What we've done at Azul is look at that. We find that in terms of the benefits of JIT compilation, over half the performance improvements that we get come from using speculative optimizations. By tracking things and figuring out how to optimize code like I've just shown you, that really does improve the overall throughput of the application. This is often why you'll see that code that's written in Java, once it uses the JVM and JIT compilation, will actually outperform statically compiled code written in C or C++, and certainly outperform statically compiled Java code. So obviously it's critical for good results. And what we want to do is we want to minimize as much as possible those de-optimizations where we fall into the uncommon trap. We have to throw away compiled code and we have to recompile it because that's extra work, and it means we're doing work that we really don't want to do. So how can we go about solving the startup speed problem? If we're looking at microservices specifically, if we want to have our services available very fast with the best possible performance, what are the different approaches that we can take to that? Well, one that has become very sort of popular, I should say, or interesting to developers more recently is Graal VM. Let's look at that. So Graal VM has been around for a long time. I used to work for Sun Microsystems when it was still Sun Microsystems, and this was a research project that was started by Sun Labs. So this goes back 15, probably even 20 years now. And the idea behind Graal VM is a high-performance runtime for polyglot applications. Sure, the JVM can deal with polyglot because you can compile Kotlin, you can compile Scala, you can compile Clojure into bytecodes, as well as Java. So it is polyglot from that point of view. But Graal VM looks at a much wider range of code and languages. And also it looks at a much wider sort of type of language. Clearly, we can run Java on top of Graal VM, and there's a couple of different ways that we can do that. I'll come back and talk about that in a moment. But then we can also deal with scripting languages. So we can use Ruby, we can use JavaScript, for example. And what they take advantage of is a thing called Truffle. And Truffle is something which is a language implementation framework. It generates abstract syntax notation for these scripting languages such that that can be passed to a compiler to generate code for that. So that's the sort of layer that takes the scripting language and generates stuff that can be passed to our compiler. For the traditional statically compiled languages like C and C++, that uses yet another layer, which is Sulong. And Sulong is built on the LLVM project. That's a compiler project, open source, which generates intermediate representation. That can then be passed through Truffle and then passed to the Graal compiler. Graal is a bit of an overloaded term here because really Graal is the compiler which has been written in Java. They call it Graal VM, but it's really the Graal compiler. And then you've got Truffle and Sulong and Substrate around that. So having compiled the code, obviously we need to be able to execute that. And there's two ways that we can do that. We can either do it if we're dealing with a Java environment through the Java Virtual Machine compiler interface and then have it work on the JVM. So this is essentially using Graal as a JIT compiler, and we still have the managed runtime environment of the OpenJDK hotspot VM. If we want to do native images where we're compiling the code directly into the platform-specific instructions, then we use Substrate VM. And Substrate VM is something that you can compile into your application to provide that managed runtime environment that you would normally get from the JVM. So things like garbage collection, things like thread synchronization, those are handled by the Substrate VM. So Graal is quite a wide thing that's applicable to this. Now, from a Java application point of view, as I said, you can run through the JVM and use Graal as a JIT compiler. But what a lot of people are looking at is, in terms of using that, it's a replacement for the C2 JIT compiler. So it's the heavily optimizing part of the compilation system. For microservices, the thing that most people look at Graal for is the idea of native images. And this is where you do ahead of time compilation. If you're using Graal Enterprise Edition, then you can use this profile guided optimization to feed more information about how the application runs into the compiler. From a simple perspective of being able to have fast startup, it works very well. So Oracle claimed that in terms of using a native image, you get 50 times faster startup than you would with pure bytecodes and just using the JVM. And they also say that in terms of the memory footprint, because you can eliminate a lot of the excess stuff that's in the JVM, then you can actually get up to 5 times smaller, according to Oracle. From the JVM point of view, as I said, it uses Substrate VM to handle the things like garbage collection, things like the thread synchronization. If you look carefully at that, how it deals with memory management, it works very similar to the G1 collector. It does some extra things in terms of hybrid region-based allocation and static analysis. But one of those things is to think carefully about how the garbage collector works and how efficient that will be in terms of eliminating pauses or not eliminating pauses, as the case may be. There's another thing called Project Leyden that was started, well, I say started, it was proposed back in April of 2020. And the idea behind this was looking at how to take a pure Java approach, OpenJDK, rather than the Graal polyglot idea. This is about just dealing with JVM-based languages and looking at how to generate static images for that. What you would do is generate a static program derived from the application, same concept as Graal, but purely for Java or JVM languages. It would be a closed world. And this is, again, one of the things that you have to consider when you're thinking about using Graal, is there are limitations on what you can do. So you can't do things like class loading at runtime because you're fixed in terms of your image. You can't do things like dynamic bytecode generation. Even reflection, Project Leyden, I believe, would have reflection, but things like reflection with Graal, they don't work in the same way. It's very much more complicated to be able to implement reflection with that. To date, nothing has been done on Project Leyden. I'm very surprised about this because there was a big fanfare when it was announced, and they haven't created a mailing list. They haven't created a repo for it. So nice, okay, great idea, but nothing actually been done on that so far. Okay, talk a little bit now about what we do at Azul in terms of being able to provide better performance and specifically fast startup. So we have a thing called Azul Prime and ReadyNow. What we've done is to basically look at the way that the JVM works and think to ourselves, how can we improve that? What could we do to do things differently? Sure, there are lots of projects that have tried different things, but we've taken our own approach and gone down our route in terms of improving things. First thing we did was decide we don't want to start from scratch. We don't want to write a whole new JVM. That just doesn't make any sense. There's lots of bits of the JVM in terms of hotspot and OpenJDK that work very, very well. So we start with that as our base, and then we replace certain pieces of functionality, pieces of code in hotspot with things that we've developed. The important thing is that once we've done that and we compile it, we run all of the TCK tests, that's about 150,000 tests, to verify that our implementation matches the Java SE standard. The important thing about that is it means that for you as a user, you don't have to change any of your code, don't use new APIs, you don't have to even recompile your code. You simply take your existing class files, jar files, and deploy them with the Prime VM rather than the hotspot VM. From a performance point of view, what we've done is to deliver and develop a higher performance, lower latency approach. From a garbage collection point of view, what we do is replace all of the collectors in hotspot, so serial, parallel, CMS, G1, Shenandoah, ZGC, replace all of those with one that's called C4, the continuous concurrent compacting collector. And the idea behind that is it is truly pauseless because none of the phases of the collection algorithm involve stop the world pauses. We can do it fully concurrently with the application threads, and we can compact, meaning we do relocate objects within the heap to eliminate fragmentation and make better use of the space that's available. From a throughput point of view, rather than using the Graal JIT compiler written in Java, we looked around and we said, okay, we like LLVM. Again, it's a very good open source project, nice modular approach, generates very heavily optimized code. We'll replace the C2 JIT compiler with Falcon, which is based on LLVM. We essentially took the back end of the compiler, made it work with the JVM and the garbage collector and so on, contributed those changes back to the open source project. The last piece of how to address performance is that warm-up time, getting that fast performance as soon as the application or service starts. And that's where we use ReadyNow and a thing called compile stashing to reduce the warm-up time. In terms of what ReadyNow does, we say, okay, you start your application in normal way and you let it run with a representative workload, or you just run it in production and let the application do all that it does until you're happy that it's warmed up and all the methods that you're using frequently have been compiled. They've been compiled with C1, they've been compiled with Falcon, and any de-optimizations have happened because we've kind of let it run long enough that we can see where we've made mistakes in our assumptions. So get to a nice steady state in terms of performance. At that point, we collect a profile. And the profile consists of 4 things. First of those is all the classes that are currently loaded. We then collect a list of all the classes that are currently initialized. Now that could be a subset of the first list, or it could be the same, but we need to know the differences if there are any between those. We also take a copy of all the profiling data that was collected during the interpreted mode and also when code was compiled with C1, and we looked at how the methods were being used. And very importantly, the 4th piece of information that we collect is the speculative optimization failures, where we made an assumption, we got it wrong, had to throw away the code, had to recompile it. Because if we know the mistakes we made in the past, we don't need to make them again in the future. Now we can collect that information at any point, meaning that we can let the application run for however long it takes to get the information we need. Could be you run the application for 2 minutes, you could run it for 2 hours, you could run it for 2 weeks or 2 months, even if you wanted to. get to the point where you're happy with the performance. Similarly, because things change over time and the way that the code is compiled and adapted changes, you can have different profiles for different workloads. Example, you could have a Monday morning profile, you could have a Friday afternoon profile, different workloads, different compile code, and so on. So what that allows us to do is take that information and use it and avoid, like I said, the problems of the de-optimizations that we see elsewhere. What we then do is when we start the application again, rather than going through that whole process from start again, we say, right, let's use our profile. We'll immediately load all the classes that we can load from that list. We'll immediately initialize all the classes we can initialize from that list. And then we know which methods are the ones that need to be compiled. So let's pass those to the JIT compiler straight away, to Falcon, with the profiling data that we had before, and compile those methods straight away using the information that we've got, plus the de-optimizations so we don't make those mistakes again. Meaning that at the point where you get to your main entry point, where the application code starts running, almost all of the work that we need to do has been done. You'll be running at about 98% of the performance level you had when you took the profile. Now, we can't quite get to 100% straight away. And the reason for that is that there are certain limitations in terms of the way that the JVM is specified. So the way that you can actually load classes and initialize classes and things like that. And the other thing that we have some limitations on, we're working on this as a different approach, is things like Lambda expressions. If you use Lambda expressions, they use the invoked dynamic bytecode, which delays the implementation of the how that Lambda expression is compiled until runtime. And that does have some implications on what we do with our compiled code. But essentially 98% of the performance, 2 or 3 transactions, and you're up to 100% of the performance level you had when you took your profile. If we look at the way that we can do that, we can also do generations of profiles. So we can profile and then profile again. And we can see that in terms of latency here, the light blue line is without using ReadyNow. So we see very high latency to start with because we're running slower. We're using interpreted mode, compiled C1 code, and so on, and going through optimizations and de-optimizations. And then we've got a first generation profile and second generation profile, which really brings that down. So we're getting very close to the ideal level of performance straight away. Now, if we simplify the performance graphs, this is not latency now, this is overall performance. If we simplify that and we say, okay, with time, without ReadyNow, we go through this gradual warm up till we get to our optimum level of performance. If we look at it with ReadyNow, now that's much better because obviously we've got a much steeper graph and we get to that maximum level of performance much, much more quickly. It's a little bit of a drawback though, you see, because there's this red line here where the application is not doing anything at all. So we get absolutely no response from our application whilst we do the compilation, whilst we do the class loading and so on. So that time is where we're doing all of that work. That's okay in certain situations, but really we want to eliminate that. So what we've done is look at how Falcon works. And we said, okay, you take your bytecodes, you generate intermediate representation for LLVM. Pass that to the compiler. The compiler then needs to understand how to optimize it, and it will issue a series of queries through callbacks to the VM and say, using the profiling information, answer this question about how to optimize the code. The VM will pass back a response saying this is how it's used, so you can optimize this way. LLVM will then generate machine code and pass it back as a compiled method. We then run that without having to do any extra work. Great. What we know, though, is that Falcon is a fully deterministic compiler. Same set of inputs, always generates the same set of outputs. If we look at a method that we're compiling, you can think of that as consisting of a certain set of data. So you've got the actual code of the method itself. So that's the bytecodes. You've also got profiling information for that. And then in order for that to be compiled, LLVM will send a series of queries and get back responses. And it will then produce machine code. So the idea is that if we have the same input, meaning that we've got the same method, it hasn't been recompiled, it hasn't been changed, and we've got the same profiling data, that will always generate the same set of queries and responses. And we know that from that, we will always get the same machine code. it's deterministic. Okay, we can take advantage of that. And what we can do now is, in addition to recording those 4 pieces of information in our profile, we'll also stash all of the compiled code. So all of the methods that were compiled whilst the application was running, we'll take a copy of that code. Now, when we start up the application, if we know that we've got the same method and we've got the same profile, then we can use that compile stash as a cache and simply say, take this method. If it's already there, don't bother compiling it, pass it back, and we've got the code. Without compile stashing, obviously we have our pause time at the beginning, and with compile stashing, we can reduce that by up to 80% in terms of compile time, up to 60% in terms of CPU load, which gets us almost to that sort of perfect graph where we've got basically 100% level of performance all the way through. One last thing to talk about is something else that we're doing at Azul. This is more of a kind of research project. It's Java on Crack. Probably not the best marketing slogan, but what this stands for is Coordinated Restore at Checkpoint. And essentially what this is doing is saying, run an application and then freeze it at that point, and then be able to restart it at some point later. And because you're restarting it, you can restart it with exactly the same level of performance that you had when you paused it, when you checkpointed it. So this is a research project. We've just started it now as an OpenJDK project. So if you go to openjdk.net, you'll find that there's CRAC as a project, crack, and you can look at the information there. It's built on top of some existing technology that's been used in Linux, checkpoint restore in user space, or queue, as it's called. That's really targeted at live container migration, and what we're doing is sort of building on top of that to allow us to do the same thing with the JVM. Key thing about this is it's coordinated. What I mean by that is that if you just said, like, let's freeze, take a snapshot of all the registers and the stack and so on, and then try and restart that, you're going to run into all sorts of problems, because if you've got any file connections open, if you've got any network connections open, that's all just going to fall apart when you try and restart your paused application. Coordinated means that the application has to take some action before it can be checkpointed. That action means you have to close any files, you have to close any network connections, but you can then say, okay, we've got to that point, take a checkpoint. When we restore, the application knows that it's being restored, and so it can then say, right, I need to restore these file connections, I need to restore this network connection, do all it needs to do, so that it then can continue with the same level of performance, but without the issues of state management, if you like. So there will be a generic crack API, so we can coordinate between the JVM and taking checkpoints and being able to restore from a checkpoint. So this is kind of an interesting approach. And in fact, we've got a sort of proof of concept thing. And again, there's a link from the OpenJDK page to our GitHub repository here. And this is using our proof of concept, which shows that the time that we can get for things like Spring Boot, I mean, this is just like crazy. So millisecond startup time for a Spring Boot without using crack, so on OpenJDK, that's about 4 seconds. Using Spring Boot, that's 38 milliseconds. Now remember, this is not like native images where you get lower levels of performance. This is the idea that you're taking a state that you've generated, so it's JIT compiled, you've compiled all the code using speculative optimizations, using aggressive method inlining, and you can then get your Spring Boot application running in 38 milliseconds rather than 4 seconds. Same with some of the other things here, actually XML transform. Okay, that's not quite as useful, but Spring Boot, I think, is a great example of just how powerful this could be. Quarkus as well, 980 milliseconds without crack, 33 milliseconds with. Just to summarize then, basically the idea of fast startup, faster code. Microservices can benefit from fast startup, but don't think that that's the only thing that you should consider, because of course the overall performance of that microservice could be more important than how quickly you can make it available at that level of performance. So sure, microservices where you're doing functions or you're doing AWS Lambdas, startup time is the most important thing. But if you're running a service that's going to be longer running, you may well think that the overall throughput is going to be better served by using JIT compilation. Consider all the aspects of Java performance, startup time, throughput, latency, and like I say, fast startup with slow overall performance might require more instances, and that might lead to increased costs in your cloud infrastructure. If you want, you can try Azul Platform Prime free for 30 days. We've got a trial download there that you can go to on our website, and you can see what's going on there. Okay, so that is the end of the presentation. So let's see if we have any questions. So let me stop sharing my screen and let's have a look at the chat. Right. Okay, good. Right. So yes, if anybody has any questions, you can either feel free to just use the interactive system, or you can write them on the chat. I am here for another 5 minutes. Okay, bit off-topic question about Azul Zulu OpenJDK. You mentioned on your website that there are open source, however, the source code is nowhere to be found online, e.g. inside a GitHub repo. According to the README inside the download JDK, we have to send an email to get it. Why is that the case? You see, that's interesting. Now, yes, we are actually in the process of trying to get our code up on a GitHub repo, and yes, we really should do that just to make life simpler. But technically, if you read the GPL, the license that is used for the OpenJDK source code, it says that you don't have to make the source code available in a repo. You only have to make the source code available to somebody if they ask for it. So we're fulfilling the terms of the license, meaning that if you send us a request for the source code, we will send it to you as a bundle, and you can request the source code to a specific build and so on, and we will send that to you. So yes, we are aware of that. We really, it's really just the engineering resources we need to get it onto a GitHub repo and keeping it updated when we do fresh builds and so on. That's a bit more work than, because we've got so many other things to do. It's not quite the top of our list at the moment, but we obviously are fulfilling all the requirements of the GPL in terms of making it open source and making it available to anyone who wants it. So I guess that would be the answer to that question. Cool. Are all optimizations Falcon C4 available only in full paid plan? Yes. So in terms of what we provide, we have our Zulu builds, which are just OpenJDK straight out of the repo, build, bug fix, and so on. But the Prime JVM is our commercial product. So Falcon C4 is only in the commercially licensed version of that. So that's the difference between those two. Okay, good. Somebody just said a very informative presentation. Thanks. I'm glad about that. I must admit, I certainly enjoyed doing this presentation. There's lots of really interesting things in terms of AOT and JIT. I do find compilation and the approaches that you can take, and optimizations as well. I find that very interesting to see how things like escape analysis work, and how you can then avoid having to create instances of objects on the heap, and you can actually put them directly on the stack and things like that. So it's kind of interesting stuff. Okay, I've got one more minute, and so if anybody does have any last questions. Okay, I believe my time is up, and I don't see any more questions. So thank you, everybody, for listening, and hope you have a good day.